Assalamualaikum and good day everyone. Today we'll be talking about line integrals, one of the 4 key theorems in vector calculus. Before we started, I would like to introduce our member ARINA ASNA, SYED ALIYA, ROZAMILA AMYZA and me SHARIFAH HUSNA. For your information, a line integrals is a powerful tool used to calculate the total effect of a field, such as work done by a force, along a curved path. It is especially useful when working with scalar or vector fields that change from point to point. The concept goes back to the 18th century. Leonhard Euler first raised the idea of summing quantities along a curve, asking if we can add distance, can we also add force? Later then, Carl Gauss explored how force vary in space, and John Green in 1828 formally linked force and work along a path. Although his work went unnoticed during his lifetime, it laid the groundwork for modern line integrals. The full formulation we use today came in the late 19th century when Josiah Willard Gibbs and Oliver Heaviside introduced vector notation and made line integrals practical for solving real-world problems in physics and engineering, especially in areas like fluid flow, electrics, and mechanical work. Now, let's take a look at the mathematical side of line integrals. First, we have the scalar line integrals. These let us integrate a function along a curve by summing value of the function weight by arc length. As we can see, below scalar line integrals, we have 2-dimension and 3-dimension formula of scalar line integrals. Next, we have the vector line integrals, often used to calculate work done by a force field. To find the work done by the vector fields F along a path C, we take the line integrals of F dot dr, which is the same as integrating from A to B, and dot product of the vector fields evaluate along the path and the derivative of the path. This can also be written in component form as the integrals over C of P dx plus Q dy plus R dz. This formula tells us how much of the force actually contribute to motion along the path. However, line integrals have conditions. They only work when the curve is smooth or piecewise smooth, the parameterization is differentiable, and the field is continuous. They make fields if the field is discontinuous, the curve has sharp corner or pass through a singularity, and for vector fields, if the field is not conservative and the path is closed, the results depends on the path taken. So, before using line integrals, we must make sure these conditions are met.
So I will continue for case study 1, which is line integral with respect to arc length. So the case study is evaluate the line integral for x square plus y square plus z square ds, where c is the curve parameterized by rt equal to sin t cos t to t for t from 0 to pi. This is the figure for this line integral. So how to solve case study 1? First, we have to find r prime t, and we get cos t negative sin t 2. And then we find the magnitude of r prime t, which is the ds. And then we get square root of 5 dt. And then we substitute r into line integral, and then we get integrate from 0 to pi sin square t plus cos 2t plus 4t square multiple with square root of 5 dt. And then we get the final answer is 99.4677. That's all.
Case study 2. Show that fzy is equal to 2xy cubed plus sin z component I plus 3x square y square j plus x cos z component k is conservative, and find its potential function fxyz. And hence, calculate the work done by f on an object moving along curve C from 4, 0, pi to 2, 2, pi over 2. So this is the graph based on the parametric equation that we will calculate soon. For step 1, we determine the parametric equation x t, y t, z t to build a graph. As you can see, to get a parametric equation, we use position vector from point 4, 0, pi and sum the parallel vector, which is the point negative 2, 2 pi over 2 times t. So we get 4 minus 2t, 2t pi minus pi over 2t. So we started answering the question in step 2. Check for conservative. We need to find cross product del cross f, and we got 0i, 0j and 0k, which is f is conservative, therefore the integral is independent of path. For step 3, check its potential function. So we need to integrate fx dx, integrate fy dy and integrate fz dz, and got fxyz equal to x square y cube plus x sin z plus z. And last, to find the work done, we can use independent of path as it follows the fundamental of theorem. There is a point FA and FB that we compute from substitution of the points that object moving into its potential function. So we apply integration of f.dr equal to fp minus fa. Since fb equal to 34, fa equal to 0, so we get the work done is equal to 34.
For the maple command of our project, I will start with case study 1, which we use restart to clear all the previous value, and then we use with vector calculus, and then to plot the graph we use with plus, and then set the coordinate to Cartesian x, y, z, and then we declare the variable which ft vector sin t, and then gt vector cos t, and then ht vector 2t, and then we plot the graph and display, and we got the graph like that. We were given rt equal to sin t, cos t, and 2t, and then we calculate the ts, which is the magnitude of differentiate rt, which is we got square root of 5, and then we integrate into the function f equal to x squared plus y squared plus z squared, which is we got equal like our manual solution, which is 99.4677. Now we'll be moving on to case study 2, which like the previous mapper command, we use restart and then with vector calculus, and to plot the graph we use with plus and set coordinate to Cartesian x, y, z, and then we set up the variable, okay, just like this, and then we continue to display the graph, and then we go like that. Okay, given the vector field 2xy cubed plus sin z, 3x squared y squared, x cos z, and then we determine the parametric equation, which is the r0 equal to vector 4 0 pi, and then v vector -2 to -pi/2, and then we calculate the r equal to simplify r0 plus tv, which is then we get 4 minus 2t plus 2t plus pi minus 1/2t. Okay, to prove that it's conservative, we use curl f, which is we got 0x plus 0y plus 0z, which is the f is a conservative, therefore the integral is independent of part. And then to check this potential function, we use fx equal to 2xy cubed plus sin z, and then we integrate the fx, and then we got like that, and then fy equal to 3x squared y squared, and then we integrate, and we got like that, and then fz x cos z, and then we integrate the fz, which we got x sin z. Okay, and then we got the f x y z equal to x squared y cubed plus x sin z. Okay. And then we calculate the work done, which is fa equal to f4 pi, which is equal to 0, and then for b, f2 2 pi/2, which is b equal to 34, which match our manual calculation. Once we got the value for a and b, we calculate the work done, which is b minus a, and then we got 34, and then we evaluate the work done, which got 34. Okay, we came to the end of our presentation, which this project helped us understanding how line integral work, especially vector field, to calculate values like that, like previous I showed. So we apply key theorems and solve 2 case studies, both manually and using mapper. So overall, we improve our understanding of vector calculus and also strengthen our problem solving and digital skills, which are useful for our future studies careers.